Good morning, pre-calculus. This is the second part of section 12-1, dealing with the introduction to limits. And what we want to do today is we want to deal with the properties and the operations of limits, which is on page 857 to 859. And what we're going to do is we're going to apply, in this case we have 4 properties. Again, the first one, just to give you guys an idea, the limit as some value of x approaches c of b. Again, this is your function. Once again, this is an example of a horizontal line. And that tells me, if you remember a horizontal line, that whole line has the same y value, which is b. So again, a lot of these very applicational to the last section, or the last video. Operations, this deals with the, in this case, the adding, subtracting, multiplying, and division and power rules of limits. And we're going to do these problems today. So all we're going to do today is we are going to find the limit of functions using our properties or our operations. So the first one we're going to look at, and I'm going to show you the whole thing, is the limit as our x approaches 3 pi over 4 of the tangent of x. All right. Once again, we got to use a little bit of trig. So the first thing we got to do is, well, we know tangent is sine divided by cosine. So again, I've set it up as a division. So in a division, that means we know that we have to find the limit as x approaches 3 pi over 4 of sine of x, and the limit as x approaches 3 pi over 4 of cosine of x. Now some of these are going to be very simple, like here. Again, we want to find what is the value of y on your unit circle as it gets to 3 pi over 4. We know it's going to be radical 2 over 2. And here, what is the value of x as we look at where 3 pi over 4 is on your unit circle? That's negative pi over 2. And if we do our simplification, we know it's negative 1. So the limit as our x approaches 3 pi over 4 of the tangent of x equals negative 1. All right? Now, number 2. Now, number 2, we're using the operations of limits. Okay, now we could have done this problem by direct substitution, but I just want you to see how the properties or the properties and operations are used in a function, okay, in finding its limit. So here we have x squared plus 5x plus 4. I want to find the limit as our x approaches 2. Now, like I said, we could have easily took this polynomial function, let x become 2 in direct substitution, and we would get our limit. But I want to go and do it by our power rules. So the first thing we do is we have 3 terms here, so we split it up into 3 limits. Okay, that's the addition one. The next thing we know is we can go ahead and do the power rules. Okay, so the limit as x approaches 2 of x squared is like saying, what is the limit as x approaches 2 of x squared? The next one is has to deal with the product one. Going back, just to let you guys see it, okay? Here is where that 5x is. 5 times our function, which is x. We can write it as 5 times the limit as x approaches c of that function. All right, that's what we did here. And then the limit as x approaches 2 or 4. That's an example of a constant, okay? Or in this case, a b. So keep going down. All right, we know that the limit as x approaches 2 of x is 2. Goes back to this rule right here, okay? The limit as x approaches c of x is going to be whatever c is. So again, we know that this is 2. Well, this is 2. So it approaches that. It's going to be 2. All right, you keep going, Vince. You're doing a good job. And if you do that, we get 18. Like I said, we could have done direct substitution here. I have no problem with you doing that, but I'm just going to show you how to do it by the operations. Next one. Here we have the limit as x approaches 2 of this function. All right, I'm going to split it up into a division. Now again, if you look at this part, we've already did it up here, so I don't have to do it again. That's 18. We could split this up, okay? So that means that's the limit of as x approaches 2 of x, plus the limit as x approaches 2 is 4. That's where we get 6, which is 3. Now again, I don't know why I have or there. I probably did it by direct substitution. And I was thinking of something else too. Oh yeah, I remember what it was. We can also take this same function and we could take this guy right here and we can factor it, okay? So I know the numerator is going to be x plus 4 times x plus 1. What are the factors of 4 whose sum is 5? We got that. Divided by x plus 4, okay? That's why I did this. That's why I wrote the or down. Again, now this is part of this. We'll probably see this again later on, especially in calculus. This is called, see this x plus 4? That is a removable discontinuity. Okay, because I can remove it out of it. Now I'll show you why in a second. So if I do this, now I'm left with the limit as x approaches 2 of x plus 1. I can do direct substitution. So 2 plus 1 is 3. Now, let me do something here just to show you guys can see that. This is an example of what we call a removable discontinuity. Okay? All right, now, what? I want to show you something. Y equals. If I take this original function and go ahead and graph it, okay, and I'm going to leave him alone for right now. And if I graph, well, I'm going to go ahead and graph him, okay? There is what that graph looks like in its original form. All right, you with me? And if you look at it closely, well, let's put it about zoom standard. Okay, that looks like a linear equation. So again, if I go back down here to this one, if I'm able to factor the numerator and factor the denominator, now if I can cancel out common factors, okay, that's the removable part. I can remove him. And if I look at my function now, and if I go ahead and graph this one, which in this case is x plus 1, you should see that the first function and the second function are the same exact function, just that we just were able to remove this power, these factors. All right, so I'm going to stop there, give you guys a little bit of an opportunity to work some of these examples out in your homework. Again, you guys can handle this. All right, catch you later.